We're going to look at periodicity, section 2.1 in the AQA syllabus, and we need to know about trends across period 3. Okay, now, so here we have got period 1 with the hydrogen helium, only period 2, so that's when you're filling the second shell, lithium to neon, and the one we're interested in at the moment is the last short period, period 3, sodium to argon, so it doesn't include any transition metals. Okay, so we need to know about the melting points and boiling points, okay, of these elements. So before we do that, we need to think about what kind of structure they are. They're talking about the elements here. So sodium is a metallic lattice, and so is magnesium, and so is aluminium. They're all form metals. Metallic lattice, so you have a positive ions in a sea of negative electrons, delocalized electrons, and metals, generally speaking, have fairly high melting point. Quite a strong structure, right? A lot of energy to break it. Now, silicon, we haven't come across silicon before, but silicon, the key to silicon is if you look, it's in the same group as carbon, so it forms 4 covalent bonds. Pure carbon forming 4 covalent bonds, well, that's obviously diamond. Silicon does the same thing. It forms like diamond, it forms a giant covalent structure, very similar in structures to diamond, except you have silicon atoms instead of carbon atoms, each one forming 4 bonds. And then these form simple covalent molecules. Oh, I first missed out argon there as well. Okay, so phosphorus, that tends to form P4. Sulfur forms S8. We'll talk about this, S8 molecules. Chlorine, you will be familiar with, that forms Cl2 molecules. And argon, because it is, right, so they are simple covalent molecules, small covalent molecules. And argon, it's a noble gas, doesn't form any covalent bonds, not even with itself. So that is atomic. It's just a simple atomic structure. They're not bonded at all. Right. So let's have a closer look now at the melting points and the boiling points of those elements. Okay. Right. So we can see here the metallic elements, sodium, magnesium, aluminium, reasonably high melting points. But if you look at sodium, that's quite low for a metal. So we won't worry too much about the boiling points. They follow the same trend, really. Silicon has got the highest melting point of all there because it's giant covalent. You've got to break covalent bonds. And then we get this funny pattern with phosphorus. So it goes phosphorus, sulfur, chlorine, argon. It goes up, then it goes down, then it goes down again. We've got to explain that trend. Okay. Right, let's talk about the metals first of all. Now, sodium will form, right, sodium lattice, you're going to form Na plus ions, and they're quite big. Okay, that's Na plus in a sea of negative electrons. Whereas magnesium, they're going to form Mg2 plus, so I'm going to, they are smaller than sodium, okay, even though they might look smaller in my diagram. Right, they're drawn smaller, so I can't draw right 2 plus in each one, but they are smaller and they've got a 2 plus charge. Right, both of those are in a sea of delocalized electrons, which I'll do like that. Now, if you look at sodium, sodium has got a lower melting point than magnesium. And there are 2 reasons for this, really. Right, first of all, the sodium only forms a 1 plus ion. That's because, of course, its electronic structure is 281, whereas magnesium forms a 2 plus ion because this electronic structure is 282. Also, the magnesium ion, why is the magnesium ion smaller than the sodium ion? Well, they both can have the same electronic structures. You're going to lose those outer electrons, so it's going to be 2,8. But sodium is going to have a larger ionic radius because it's got less positive charge in the nucleus. It's only got 11 protons pulling in those electrons, whereas magnesium has got 12, so it's going to be smaller. So not only is magnesium more highly charged, but it's also smaller, so it's got a higher charge density. Than has sodium, and that means it's got a stronger attraction to the delocalized electrons, and that means you need more energy to break it up. So it's got a higher melting point than has sodium, and they quite frequently ask that. So it's all to do with the size of the ions and the charge density on the ions. You may think then, quite reasonably, shouldn't that trend continue for magnesium, because aluminium 283 is going to form an Al3 plus ion. Again, that's going to be a lot smaller than the magnesium ion, because aluminium has got 13 protons, but you don't get the continuation of the pattern there, because something to do with the crystal structure, the way the ions are arranged. But don't worry about that. You don't expect it to know that, but you are expected to know why, and they quite frequently ask that, why sodium has a lower melting point than magnesium. Both crystal metallic lattices, higher charge density on the magnesium zone. Okay, so that's that. Right, silicon, let's just say a few words about silicon. I'll just get rid of that. All right, so silicon, you can see there, has got a melting point of about 1800 Kelvin or something. Right, it's pretty high, because the silicons, right, they're arranged in tetrahedrals. You have one like that, and each one of those is bonded to another silicon, 4 silicons, and each one of those is bonded to 4 others, and so you get a structure very like diamond. Both in group 4, as we said, both form 4 bonds. The melting point is not as high as diamond. And the reason for that is, well, when you melt diamond, you have to break covalent bonds. When you break silicon, when you melt silicon, you've got to break covalent bonds. But the silicon-silicon bonds are not quite as strong as the carbon-carbon bonds, because they're a bit longer, because silicon is a bigger atom. And so the covalent bonds are going to be a bit longer. Longer covalent bonds means they're always going to be weaker. Anyway, don't worry too much about that, but it's just giant covalent. Right, now let's get on to the phosphorus to argon, which has got this interesting trend in melting points. Okay, so if we look here, just draw it here. Phosphorus is there. It goes up for sulfur, goes down to chlorine below the level of phosphorus, and then it goes down again to argon. Right, what causes that? It's, well, if we think, what have we got there? As we said before, phosphorus tends to form P4 molecules, okay, whereas sulfur forms S8, and chlorine forms Cl2 molecules. So you can see that sulfur is going to have the highest boiling points and melting points, because the van der Waals forces between, and that's all you're going to get, because obviously not polar, between S8 molecules is biggest. Why is that biggest out of the lot? Because, well, they've got the most electrons. Then after that, it's going to be P4. Then after that, it's going to be chlorine, because there's only 2 atoms there. And finally, the smallest of all is going to be argon. And that's why you get that trend. It's due to the size of the van der Waals forces, which is a reflection of the size of those molecules, the size of the electrons they've got. Okay, so that's all we really need to worry about. Interestingly, let's just think about phosphorus. Okay, so phosphorus is in group 5 of the periodic table, and above phosphorus is nitrogen. That's phosphorus. Now they both like to form 3 covalent bonds. Nitrogen forms a triple covalent bond because that's very strong. But phosphorus does not like forming a triple covalent bond to another phosphorus because it's pretty weak. So it's much better for phosphorus to form 3 single covalent bonds than 1 triple. So what phosphorus does is you get like 3 phosphoruses like that, a triangle, and then you get, I draw this one a different color. That one is sort of like the top of a pyramid, and that forming, so you can see that every phosphorus there is forming 3 bonds. Incidentally, that explains why you probably know that phosphorus catches fire very easily. That's white phosphorus. It's very reactive, and the reason why it's very reactive because there's a lot of those bond angles are very constrained, and so it's quite easy for them to break open. So the activation energy is pretty low. So phosphorus will burst into flames in oxygen without having to light it or anything. Sulfur. Now, why does sulfur form S8 molecules when it's in group 6, and we know the other group 6 element, which we're familiar with, oxygen, likes to form 2 covalent bonds. That forms an oxygen-oxygen double bond. Why doesn't sulfur form that? Well, again, it's because a sulfur-sulfur double bond is extremely weak. It's nothing like as strong as 2 single sulfur bonds, so it doesn't form, whereas the oxygen-oxygen double bond is pretty strong. So sulfur likes to form 2 bonds, 2 singles, so it tends to form these rings of 8 sulfurs. So there's 8 sulfurs in a ring, each one forming 2 covalent bonds to the neighboring ones. And these rings tend to stack up on top of each other like this. So that's why sulfur forms these long, thin crystal structures in sulfur. Again, it's because what makes it form S8 is because the SS double bond is extremely weak. Now, also in this, that's all we really need to know in this topic. It's extremely short, but it does ask you to talk about the trending atomic radius as you go across. So if we just do, let's have a look at this. We'll go back to this diagram. Right. Atomic radius. Right. Forget all this stuff here. Well, period 2, it's obviously period 3, sorry, it's only the 3rd shell which is being filled. So, it's 281, 282, etc., etc., 287. Finally, up Argon 288. Right, and if you go to after Argon, you get potassium, of course, which should be 2881, and then you'd have to start a new shell. Okay, so the atomic radius of these elements actually decreases as you go across. And the reason why it decreases is because you're still filling the 3rd shell all the time, but as you go across the period, the nuclear charge increases. So argon will have the smallest atomic radius, and then you get one bigger, then you've got to start a new shell at potassium, so all of a sudden the radius goes much bigger again. So you get that's the trend there. Finally, in this topic, it asks you to know the trend in ionization energies as you go across. Now, that is covered in a separate topic, so I'm not going to just repeat it here, but needless to say, you get a pattern just very quickly, right? You get sodium's got a pretty low, magnesium is higher because the nuclear charge is then it will drop down because you are now filling the P subshell for aluminium. Goes up for phosphorus, up for silicon, sorry, up for phosphorus, goes down for sulfur because you're getting the pair repulsion effect, up for chlorine, up again for argon. Before you go to sodium, it will drop right, not sodium, potassium, it will drop right down again. Anyway, I won't talk about first ionization energy because that's covered in other videos and it's on a separate topic really. Okay, So we'll leave that there.